This video we will talk about linear inequalities, how to solve and graph them for the most part. So the first thing we need to do is talk about this word inequality, and we will have four inequality signs. We will have less than, we will have less than or equal to, we will have greater than, and greater than or equal to. So what this means is that if we have a less than sign, when we graph, we will quote unquote shade to the left of whatever number we're looking at. And if we have a greater than sign, we will shade to the right. Now, as I say this shade to the left, shade to the right, it is super important to remember that we really want the variables to be on the left-hand side here for these. It just makes it easier to understand. I will prove this in the next slide. That being the case, we also need to know how to graph these inequalities, and we will do so on a number line. So if you have either of these symbols, either a less than or a greater than, when we start graphing this, we will use what I will call an open dot. And if you have either sign with an equal to, we will use what I'm going to call a closed dot. So this is open and this is closed. And like I mentioned a few seconds ago, we would shade left. Well, we would be shading left from an open dot or left from a closed dot, or maybe you're shading right from an open or a closed dot. I think you'll pick up pretty quickly on the examples in a minute. But before we get into actually solving, a note. We solve linear inequalities like linear equations, except, this is your warning, if you multiply or divide by a negative number. If you do multiply or divide by a negative number, the inequality sign changes direction, and therefore we would need to change which way we shade on the graph. Let me go to the next slide here to explain why we like the variable on the left. So I have three simple linear inequalities here, and I want to explain why we like this and not this. So the first thing, this very first inequality here, we can take a look at that. We say x is greater than 3. And that's very easy to fulfill this inequality. I could ask you, hey, give me a value in x so that x is bigger than 3. And you could say, 4, 5, 6, basically anything that is just a little bit bigger than 3. You could also pick 3.000001, and that is still bigger than 3. And we can do something similar for the next one. X is less than -5, so you just need a number that's less than -5 or to the left of -5 if you want to think of it. We could have -6, -7, -8, -9, dot, 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 as long as it is less than -5. Now, this last inequality. Here, if you look at this inequality, it reads 100 is greater than or equal to x. And that is true. You read this exactly like this. 100 is greater than or equal to x. And if I ask you what number will make this inequality true, I get a lot of students that say, 101, 102, 103. And those numbers are greater than 100. And it's because we are saying it in this order, 100 is greater than or equal to, that really prompts students to want to guess numbers that are bigger than what's in our inequality. Let me show you what happens. Let's say you pick 103. 103, what you're saying is 100 is greater than or equal to 103. And that is not right. That is absolutely false. So what you need to do is you need to pretend that x is on the left side. We need to rewrite this. So let's pretend there's like a little mirror here, and we're going to reflect this whole thing. So this would be similar to saying x is less than or equal to 100. Well, now hearing it like that, x is less than or equal to 100, it is much easier to find numbers that work with that. We could even pick 100 here. So we could pick 100, 99, 98. We could pick pi even, 3.14. That's less than 100. As long as it's a number that's less than or equal to 100, we are good. Let's look at some graphing examples. All right, on this slide, I just want to take a couple minutes to graph a few basically already solved linear inequalities. The first of which you can see here is x is less than 3. So I'm going to do this with black ink here. And one thing that I like to do is only plot the important number. So I'm going to have 3 here. That's the first step. Need to have the important number. The next step is, do I need an open or closed dot? And because I see no equal to here, this tells me this will be an open dot. So an open dot on a graph will look like this. I usually put mine above the line a little bit, above the number line. This is an x-axis actually, and above the number line there. And I have x is less than 3. So I can just tell less than 3. Numbers less than 3 will be to the left. And so here is the graph for the first example there. And we can do something very similar here for the red example. So in red ink, I have a number line. I'm only going to plot the number that I care about here, and that's 5. And this time I have a greater than or equal to sign. So for my second step, I know I'm going to have a closed dot because of that equal to. So do that. And then since this is numbers that are greater than or equal to 5, that means I will be going to the right. So there is the graph for the red one. And lastly, this one is fun. This blue example here. This one has 2 numbers. So I have a negative 97. So I'm going to put both numbers on this number line here, and I've got 291. So since we have 2 numbers, we will also need 2 dots. This dot will be open, and it will belong with the negative 97. This dot will be closed and belong with the positive 291. So I'm going to come down here, it'll be open here, and closed here. And what's important to note here is that x is between these 2 numbers. So when we quote unquote shade, it'll be between these 2 numbers. And that's it. That's the graph for this last one. Now we're going to move to solving inequalities and graphing the final answers. So, second to last slide. All right. Again, solving linear inequalities is very similar to solving linear equations. You can think of this symbol here, and for the second example, this symbol here, you can think of them like equal signs, since that's what probably most of you are used to. We will not write an equal sign. We will keep writing the sign that is given to us. But just like any other example, if you are trying to solve for x here, you would simply just first add 5 to both sides. So I'm going to add 5 to reduce that to 0, and I'm left with 3x is greater than or equal to 24. I will then divide by 3 to completely isolate the x and get x is greater than or equal to 8. So now, using our graphing ability, I'm going to plot this number 8 on the number line. There it is. I see I will have a closed dot here. And since it is greater than or equal to, I will be sure my graph goes to the right. So here is the answer in inequality form, and here is the graph of the inequality. Now, why is this important? Well, I haven't gone over this yet, but we call this a solution set. All of the numbers that are equal to 8 or greater will make this original inequality true. So you can pick any number that's 8 or greater. So I think I first want to pick 8 just to make sure. So let's see, 3 times 8 minus 5 is greater than or equal to 19. So I'm picking 8 and I'm putting it back into this inequality just to check if it's true. So I have 3 times 8 is 24, minus 5 is greater than or equal to 19. 19 is greater than or equal to 19. Yeah, that's true. 19 and 19 are equal, so this is a true inequality. Now I'm going to be real wacky like I normally do, and I'm going to pick a really big number. How about 112? And I just want to see if that's true as well. Let's check 112. 3 times 112 minus 5 is greater than or equal to 19. Well, let's see. 3 times 112 is 336 minus 5 is greater than or equal to 19. Yeah, I don't even need to finish this. 336 minus 5 is definitely greater than 19, so that also works. But this is really powerful. It says any number that's greater than 8 will make this original inequality true. All right, next example over here. We have negative x is greater than 5. Now you might look at this and say, oh yeah, this is already solved. X is isolated. Well, not quite. We have this negative 1 being multiplied to the x. So we need to divide by negative 1 in order to get the x isolated. So that means we'll have an x, and 5 divided by negative 1 is negative 5. But because we divided by a negative number, the inequality sign changes direction. And I write it big and obnoxious like this so that you see that it changed direction. And again, that only happened here because we divided by a negative. Over here, we divided by something. We divided by a 3. It's not negative, so the sign didn't change directions. So then you can graph this. The important number here is negative 5. It's open and it goes left. There we go. I have a couple more examples here. All right, last couple examples here. We have a linear inequality here on the left in blue. So we're going to solve and graph this, and I think what I first want to do is to subtract 2x. So I can reduce the 2x over there. And again, I'm moving these x's to the left side because I like having my variables on the left. So this will be minus 7x plus 3 is greater than 3. Then to isolate the x term, I need to subtract 3 from both sides. That reduces, Don't freak out. It's not a big deal. Just 3 minus 3 is 0. But then to isolate, kind of like what we did in the last example, we have to divide by negative 7. So we will have x is less than 0. And if you want to graph that, it'll look something like this. It'll be open and going to the left. Okay, last example here. This is what we call a compound inequality. It's not that bad. If you let's see, if you cover this piece up and look at the negative 3x plus 10 is less than 28, you have to think about how you would solve that piece first. And really, then what you would need to do is just subtract 10. But since there is a second inequality sign, we would also have to subtract 10 here. So we are subtracting 10 because we're still trying to isolate the x that is in the middle. So this would be negative 3x. Over here we would have negative 17, and over here we would have 18. Lastly, we need to divide by negative 3. And again, dividing by a negative. Negative 17 divided by negative 3 is 17 over 3. Negative 3 over negative 3 leaves me with an x in the middle and a negative 6 over here. But we divided by a negative, so the inequality signs change direction again. Now this is a little odd. This notation here, we really like having less than signs if you have a compound inequality. So I can rewrite this like this. And then we can go ahead and graph. So I will have negative 6 with an open dot. I will have 17 over 3 with a closed dot. And x is between those. Now, one final thing about this last graph is a lot of times you might be doing this work online, or you might have a number line already printed there that has only whole numbers listed. And in that case, you would need to know that the graph looks something like this. That this mark right here is 17 over 3, and that is between the whole numbers 5 and 6. So just beware of that as you are going through and working through any exercises that you might have available to you. I very much hope that this video helps you understand solving and graphing linear inequalities a little more.